Orbital rings represent one of the best ways to get people off a planet. They also happen to be handy if you want to build a planet, too. So today's topic, Orbital Rings, is the culmination of this series, especially the concepts we've discussed in the last two episodes, launch loops and space towers. You don't have to have seen those first, but I spent more time explaining the basic concept of active support in those. The Orbital Ring has so many applications, I didn't want to spend much time repeating the basic physical concepts in favor of exploring those. I've talked in passing about the Orbital Ring before. Indeed, we covered it briefly in one of the oldest episodes on the channel, and I regret being brief there because we bypassed so many of the uses these things have. This series has been mainly focused on getting into space cheaper and safer, and we have discussed some systems that are so much cheaper that they can be used to get people up into space at prices that make it affordable for an average person to take a vacation up in space. The Orbital Ring goes far beyond permitting more scientific research or expensive vacations though. It is a system that genuinely allows people to commute to space for work in the morning and still come home for dinner, and spend no more for a ticket to orbit than you would for a train or plane ticket to a neighboring city. We've discussed the concept of active support and dynamic structures before, and in a good deal of detail in the last couple episodes of this series, so I will keep the review this time brief. Normally, materials provide passive support. The forces which bind molecules together or keep them apart keep a material from ripping apart under tension or smashing together under compression. Some materials are stronger than others. It is very easy to rip apart tissue paper, and far harder to tear apart Kevlar. But even supermaterials like carbon nanotubes and graphene have their limits, and we have yet to mass produce them. We have an alternative way to hoard stuff up though. We can push on it. That's what keeps a sheet of paper hovering over an air vent, or a helicopter hovering in the air. In the last episode, we looked at keeping things in place by bouncing materials upward inside them, allowing super tall structures. But the Orbital Ring uses a different method more akin to what we saw in the Lofstrom loop, but still a bit different. When I place something in a stable circular orbit, it has a speed based on the mass of the object it is orbiting and the distance it is orbiting at. That's around 8 kilometers or 5 miles per second for the area of space just above our atmosphere. It actually drops as you get further away, just 3 kilometers a second when you get out to geostationary distances, slow enough that you orbit at the same speed the Earth turns on its axis, so that you stay above the same point. Further out, at the Moon, the speed is about 1 kilometer per second, and drops the farther you go until you are no longer bound to Earth gravitationally. We haven't been much interested in this series with space beyond low orbit, let alone beyond geostationary, but we are today, so keep that in mind. It's the speed that matters, not the angle. You can orbit Earth around the equator or from pole to pole at the same speed. But each orbital path is a unique thing, and any object on that same path, with that same speed, won't seem to move relative to anything else on that path. Which means if I'm in orbit of the Earth in a spacesuit and let go of a flashlight I was holding onto, it will seem to just sit there next to me, unless I gave it a little shove, in which case it would drift away. So I could put several objects in the same orbital path and they'd sit there together unmoving, relative to each other. They'd still be zipping around the Earth at high speed, but then so are you and everything in your home, zipping around the planet and on the planet around the Sun, and around the galactic core too. Everything is moving, but it is relative motion. If I were standing on one of those objects, I could lay a bridge down to the next and walk over just fine, though since we are in freefall, I'd basically float, not walk. I could extend this all the way around the orbital path as a big ring. This orbiting ring would travel around just fine, but it is not much use to us as is. On that same note, if I had a perfectly rigid material, I could construct a ring out of it around the Earth, and it would just hang there, even without orbiting, because all the gravity on it would cancel out. This would be quite useful since it would be stationary to the ground, if unstable. Also, we have no perfectly rigid material, so it would sag down to the planet. The one orbiting would not, since it experiences no gravity, or rather its inertia or centrifugal force cancels that gravity out. It is also technically unstable, but we can fix that, and in a way that makes it more useful too. We'll get to that shortly. So far so good though. I could make a nice metal hoop around the planet, and if it was spinning at orbital velocity, it would stay in place. Now imagine for the moment we stuck a bunch of magnets on this metal hoop. Actually, since it is a big piece of metal, we probably wouldn't need to put any magnets in it, just run electric current through it, but let's keep it conceptually simple for now. The ring has a bunch of magnets on it. Now I build a big space tower next to it like the ones we discussed last episode, and I reach out and put a magnet over some spot on the spinning hoop. The hoop is spinning around very fast, whereas I am stationary to the Earth, so if I touched it, that hoop would slice through me like a circular saw. But it won't be touching that magnet, the magnets on the hoop will be pushing back against it. That's not terribly stable, but if I took a bracelet with magnets on it and opened it up and clapped it around the orbiting ring, it would just hover there. If I put some more on, they'd hover there too, and I could put some platform there and stand on it. This would be different than before, because before all those objects were in orbit too. These are just hanging right over the Earth. The ring is orbiting, but they are not. So when I stand on my platform, I feel gravity almost as much as on Earth. I could take this bracelet and extend it around the ring to make a second ring around my orbiting ring, and it would not be moving relative to Earth. I could walk around the entire thing just like I was on Earth, only high up. Nowhere and gravity is a bit weaker. I could even build an airtight house up there. As I added weight though, I noticed the orbiting ring was beginning to sag a bit. See, that ring has just enough momentum to stay in place, in orbit, on its own. Now I'm adding mass that isn't moving, has no momentum, and the system, the orbiting part plus the stationary part, needs to have enough momentum to stay in orbit. I could go ahead and get my stationary parts up to orbital speed, fixing the problem, but that kinda defeats the purpose. Instead, I can add more momentum to the ring, speed it up a bit beyond normal orbital velocity. Now the whole system has just the right momentum to stay in orbit, even though the orbiting ring has a bit too much, and the stationary part not enough. This is the basic concept. I take a hoop of metal, a millimeter thick or a kilometer thick, and spin it around the planet at orbital speed. If I run some current through it to make it a magnet, or am using a ferromagnetic material like iron or nickel, I can now float things over it by spinning the ring a little faster. The circumference of Earth is just over 40 million meters, so if I made such a hoop out of a standard thin wire, say 25 grams a meter, that hoop would weigh 1,000,000 kilograms. Way too much for a single rocket to lift up, but you can bring it up in segments and solder it together, it's just wire. Indeed, we can fly up next to it and add more wire, more strands, since if we're in orbit it just seems to be hanging there, so we can add to it as we want. We can also spin it faster to let us add more weight suspended above or around it. Now a spinning ring that we start spinning faster than orbital speed is going to have more centrifugal force added to it, and if we get enough of that, it will rip the ring apart. But for the moment, we have a spinning ring inside a stationary pipe that's magnetically kept afloat from touching it. That ring is over 40,000 kilometers long, the rough circumference of the Earth. A space elevator is about the same length, and unlike a space elevator, this is just wire, plain, regular old wire, nothing special about it. Nothing special about the conduit around it either, except that it's got magnets on it, and we can make those electromagnets so that we can run power through them and use that to speed the ring inside up, or slow it down if we need to add or subtract weight from the whole thing. We can hang some solar panels off to the side, attached to the conduit, to provide for that. We now have a solid ring in space, not seeming to move relative to the ground below, with a power source that can let us add weight to it. Now the outside isn't moving relative to the surface of the Earth, so we could have this at pretty much any altitude we wanted. One of these would walk just over the ground, but we will say it's about 80 kilometers up, same as the Lofstrom loop. We could drop a rope down from there and someone could climb up from the ground. Now a regular rope couldn't handle that and no one could climb that, but we have plenty of fairly mundane substances that do have a breaking limit of more than 80 kilometers. We're not sure if stuff like graphene can handle going up tens of thousands of kilometers, but we've got plenty that can handle tens or hundreds of kilometers. This includes those that can handle having current run through them, or are strong enough to let us bolt some wire to them at least. So we drop a cable down to Earth with a wire in it, and some elevator with an electric motor grabs that cable and its power cord and uses that to pull itself up to the ring. Power can be supplied by some other solar panels up on the ring or down on the planet. Even without superconductors, we can run an electric cable 80 kilometers without losing too much power. Which conveniently means we can run power from all those solar panels on the ring, where there are no cloudy days, down to Earth too. But never mind that for now. This is the basic orbital ring. It can be scaled up. You can make thicker rings or add more rings right next to it, though in practice you'd want to have every other one spinning backwards in retrograde orbit. They wobble too, so rather than running cables straight down, you'd often want to angle them like guy wires. But that's better than okay, because they don't all have to run out at the same angles, so you could have wires stretching a few hundred kilometers off to connect straight to cities, and those can be quite solid wires you could run cable cars up, or scaled up enough, entire trains. They can just move at normal speeds too, like any train or tram, not causing sonic booms or threatening to blow up cities if they fall off. You could build wide platforms up there with domes and people could walk around on them just like on Earth, since there is gravity. You could hang structures from them too, like the Analama Tower, now suspended from a cable only 80 kilometers long, not tens of thousands. Indeed, so long as you keep a vacuum in that conduit, you could hang the ring just over mountain height. You could put massive solar farms or regular farms up there and bring that power or food down to Earth. You can bring all the mass you want up from Earth for no more cost than the production and maintenance cost of the cable cars and solar panels powering it. Nor does that inner spinning element need to necessarily be a wire under lots of strain if you spin it up too fast. You could use big particle accelerators. But this brings up another important point: what you do once you're up there. Truth be told, you don't need any other applications. An orbital ring of this type lets you zip around the planet and up to orbital heights and down to other spots quite cheaply, but you are just at orbital height, not orbital speeds. Step off the ring and you will fall down, though you will just fall down, not re-enter. So if you have a pressure suit, oxygen mask, and a parachute, you could survive. I imagine ring diving would be a popular sport. Why are these good for space though? Recall that when we discussed mass drivers, I said the track needed to be mostly straight because at orbital speeds your turning radius is huge, unless you want to be pancaked by centrifugal force when you turn. Mass drivers and Lofstrom loops had to be thousands of kilometers long just to allow 3g acceleration to normal orbital speed. They need to be much longer if you only want to do 1g, normal Earth gravity. But an orbital ring offers us a couple of unique advantages. First off, it goes around the entire planet, so that is your turning radius if you're trying to build up speed to launch away from the Earth. Totally non-coincidentally, the turning radius for an object at that altitude for 1g of acceleration is exactly orbital speed. That's why you are on freefall when orbiting. Now centrifugal turning force acts outward, while gravity pulls inward, so a ring around the planet has those two forces in opposite directions. That means if we strap a vehicle to the ring and start speeding up, running around in circles, the force of gravity is cancelling out that centrifugal force. Indeed, if we were pulling 2g's of acceleration, we could stand on the ceiling of our vehicle, or just flip it over, and feel like normal gravity, only upside down. We could build up to 11 kilometers a second like that, the escape velocity of Earth. 8 kilometers a second will get you into orbit, but it takes 11 to escape out past the moon. Those ground-based systems like mass drivers and launch loops usually aim for 3g's as pretty safe for most people. With gravity cancelling out one of that, we could do 4 on the ring, and be doing 16 kilometers a second when we release the ring, at whatever point we want. It is a circular track after all, so we can do loops, and fly off at 16 kilometers a second. A decent speed for interplanetary travel even if you don't have rockets to help, which you would since you can bring all the fuel you want up to that ring. Most of the solar system is reasonably close to in line with our own equator, so you are fairly close to the right direction north or south when you let go of an orbital ring around the equator. But these rings don't have to be around the equator, they can be at whatever angle. You could have another one at a different angle just above or below your own and take an elevator to it, or to another one even further up. So you can take off from Earth even faster if you don't mind doing more Gs, and freight can handle a lot more than passengers. And you can also take off from a ring further up. As you get further from Earth, you lose a bit of that gravity advantage cancelling things out, but you gain more turning radius and you are further up in the gravity well and won't lose as much speed leaving it. You can build as many rings as you please at any angle or height you want, and so long as the space between the two rings isn't so high that a cable between them would need to be super strong, you just take the elevator to the next ring up. Out at geostationary, 42,000 kilometers from the center of Earth, there's not much gravity left, but 1 g of acceleration will get you 20 kilometers per second of speed, and 4 g's will get you 40 kilometers a second. That's the escape velocity from the solar system, and that is 3.5 million kilometers a day. Not a bad interplanetary speed, even if you are only using fuel to slow down. This doesn't include the Earth's own orbital speed around the Sun either, of about 30 kilometers a second, which is quite a nice boost since everything further from the Sun is moving slower. You don't have to stop there either. You could build these rings all the way out to the Moon and beyond, and you could fly off from those at 60 or 120 kilometers a second for 1 and 4G respectively, having never burned a drop of fuel, sailing out at 14 million kilometers a day, a speed that will get you to Mars at its average distance from us in 10 days. You can slow down with these too, in the same way. You are not touching the ring when speeding up, you are using electromagnetic propulsion to avoid friction, and you don't need to touch it to slow down either. Indeed, you could just have something running around on the ring at that speed, shoot a tether out to harpoon an incoming ship, and slow it and you down the same way you sped up, so long as the tether is decently strong. The exterior shell of a ring doesn't have to be stationary either. You could forego the sheath or even have the sheath spinning and the inner wire staying stationary. A ring like that next to a stationary ring might have some advantages for moving ships too. You match speeds with your train and jump on over. Those cables in the atmosphere connecting the ring, or the bottom ring to Earth, would tend to be pretty numerous since any town who could afford one within a couple hundred kilometers of a ring would probably want one. You really don't need to worry about wind or lightning in these things, but you can just attach them or reel them in during bad storms. The rings only need a little force to keep them from wobbling, so even a few cables is enough, and you'd have hundreds if not thousands connecting to each ring, so reeling some in during storms is no big deal. I imagine by now you can start seeing why I always refer to orbital rings like a whole different level of space launch technology, and we aren't done with the cool advantages yet. But so far, we've mostly been talking about small ones, or just their use alone or with other rings. Before we scale up and talk hybrids, let's talk safety and cost. As to safety, for the smaller ones, that inner ring is spinning faster than orbital speeds, so if it gets damaged and flies out, probably shredding part of the ring in the process, it will fly out, not down, and those bits which don't will burn up in re-entry. The stationary part will just fall. But as with previous systems, we can attach explosive charges to break it into smaller bits and let parachutes slow those down. That option is totally out the window for the bigger ones we will get to in a moment, but those are much sturdier since they'd have tons of rings that supported them, not just one. As an example of hybrid tech though, while we can place another ring right below and at an angle to a ring so that it might fall to rest on its neighbor, we can also use the Atlas pillars from last episode to run straight up beneath the ring like normal support pylons, though they need not run up straight either. Of course, you could just bypass the internal spinning rings or particles with these, just one big suspension bridge running around the planet or just part way, or even at angles. But the ring is better, and the Atlas pillars just allow a nice addition of capacity and safety. As to cost, that's another story. Once the first ring is in place, you can use it to bring all the rest up quite cheaply, but that first ring probably needs to be fairly sturdy, and mass at least several thousand tons. so it is essentially the same price range as bringing up a basic space elevator. Same concept too. You get a simple small one up and use it to bring more mass up. More expensive than a space elevator though, since those assume super strong and super light materials. The orbital ring is just copper or iron, cheap but expensive to get into space. This is one of the reasons mining and industrializing the moon, with its huge quantities of raw materials and negligible gravity and atmosphere, is very attractive to us. It is just as useful, indeed arguably more so, even with an orbital ring making freight costs up from Earth cheaper, but it makes it far easier to build that first orbital ring, especially if you want to be a decently large and handy one. I would be a lot more confident bootstrapping more rings from a first orbital ring, a meter or more thick, massing a couple tons per meter of length, than a hair-thin wire, and at a circumference of 40 million meters, such a ring would mass in around 100 megatons, more mass than everything we've lifted to orbit combined. But better to start that way, and so better to use the earlier and more modern systems we've discussed to get to the moon and asteroids first. When colonizing the West Coast, you start with the Oregon Trail, not a massive 3-lane interstate freeway after all. So this is definitely not your next step in making space cheap. Nothing offers cheaper cost per kilogram launched, but it takes a lot to set up, and its real advantage is throughput, not cost per item launched. Only the space elevator even gets into the ballpark with orbital rings on that score, and that does require materials we don't really have. The orbital ring, on the other hand, while quite a feat of engineering in every respect, relies on only modern tech, though a power source like fusion and access to room temperature superconductors makes it a lot better. You don't just build one either, you build a bunch at different angles around the planet, with cables running off to any place that wants one. The orbital ring network makes a nice launch point for interplanetary travel, but it's even more phenomenal for intraplanetary travel. You take a cable from your town to orbit, at whatever speed local law permits, arriving in less than an hour even if it's a wide angle, long cable and limited to subsonic speeds, and from there race around to your exit ramp at hypersonic velocities. If those rings are big enough and those cables sturdy enough, it's not just passengers traveling anywhere on the globe in a couple of hours, it's bulk freight by the megaton doing it too. Scaled up, one of these ring networks can handle billions of people and billions of tons of cargo moving to and from space every day. And you really can scale these up too. That guy wire going to the ring could instead be a big highway with a domed tunnel over it you could drive your car up. Those rings don't have to be meters wide but could be kilometers, and if they are low enough in the atmosphere to gain some protection from meteors and space trash, which you are at 80 kilometers up, you could just dome over places and walk around with regular old air, sunlight, and gravity. You wouldn't have to stop your car drive when you arrived either, or your walk. People ask sometimes about being able to connect a space elevator straight from the moon to Earth, and you can't, even with a super strong material, because the moon is tidally locked to Earth, but not the other way around. You can do that with Pluto and Charon, for instance, since they are both locked to each other and always show the same face. With an orbital ring, you actually can do this. Orbital rings don't have to be perfect circles for one thing, but that's not what I mean. You've got a stationary ring around Earth, just above the atmosphere or way out at geostationary or even further. Once you're up at geo though, the strength of gravity is so low, you don't need strong materials for 1,000-kilometer long tethers anymore, so you could easily build one up from the ring out to the moon's orbit. We could put a ring there too, but more importantly we could have an elevator come off the moon, stretching all the way to the ring at geostationary. That ring's sheath doesn't need to be moving at normal geostationary speed, nor does the tether to the moon have to stay fixed. You don't even need fancy magnetic connections either. The moon only goes 1 kilometer a second. We can actually make traditional mechanical connections that can handle such things. So yes, with an orbital ring network, a big one but not a high-tech one, you could grab a train from your hometown wherever on Earth and step out of it on the moon somewhere. I imagine you just take a ship from the first ring instead, or one of the higher ones closer to geostationary. Those already offer launch speeds fast enough to let you make that trip in under a day. The 4G shot off a geostationary one would get you there in 3 hours, but you could actually walk from Earth to the moon with this kind of network, though you'd need magnetic boots once you got far from Earth's gravity well. Though you could also make the connection between the rings be hollow spinning tubes with spin gravity too. You can also scale this up to go between planets. A bit silly, but possible. I remember some years back before I started the channel and used to play with more extreme forms of megastructures, not the ones we've covered on the channel, those are all basic ones, even the solar system sized ones. I tried coming up with a way to walk, swim, sail, or fly between planets, and orbital rings and dynamic structures do actually let you do crazy stuff like that. More down to earth, literally, they do let you wake up in the morning at home and commute to space for work. And you can make a lot of living space in low orbit too. There's a game setting called Warhammer 40k or 40,000 set in the year 40,000. Many of you are probably already familiar with it, and it features Earth, called Terra in that, as a galactic capital home to trillions, an example of an ecumenopolis, which we've discussed before. In that there's something mentioned called an orbital plate, which is described as a small continent floating over the planet, and they've got several. No real details are given about them or how they hang out there. They do have anti-gravity in that series though, so probably that. But orbital rings let you do stuff like that. Indeed, you could stick a bunch of them, all wide and at different angles and slightly different height, up over a planet to totally enclose it. Lay down some mesh and some dirt and water and air, and you've got a new planetary surface. You could do something like that around a gas giant like Saturn and produce what is called a supermundane planet, or shell world. You could do several concentric shells around Earth and produce what we call a Matryoshka shell world, both of which are discussed in the episode Shell Worlds from a couple years back. I was going to say with orbital rings the sky's the limit as to what you can do, but that's not really a good saying considering the sky is specifically not the limit with them. If you've got enough power and can use it without too much waste heat being produced, basically if you've got good superconductors and fusion, you can build some truly monstrous stuff. Particularly since the Atlas pillar variation we discussed last time lets you make straight lines, not just curves, and orbital rings don't have to be circles, and you can change these things' dimensions. That's part of why we call them dynamic structures. I think by now you can see why I saved orbital rings for last, and why I've spent the whole series talking about how much more awesome they are than the other concepts for getting stuff into space cheaper and safer. Now, I'm not formally closing out the Upward Bound series. We may revisit it more in the future. We've got tons of concepts we haven't covered yet, and others we could cover in more detail that just showed an episode with a few other related concepts. However, this ends the series for now and the main sequence of it. We've looked at space elevators and skyhooks and mass drivers. We've talked about ways to improve rockets by making them reusable or giving them better power sources like atomic ones or metallic hydrogen. We've looked at 1,000-kilometer-long floating launch loops and runways suspended from towers so tall they don't just scrape the sky but rise over it. Now, finally, we see the orbital ring. I don't know what technologies we will see in between modern rocketry and this concept, but barring a big game changer like anti-gravity or wormholes we can open up from planet to planet like in Stargate, I think this one is the final product of the effort to get people off the ground and up to the heavens. Even things like cheap, compact fusion we could make spaceplanes with doesn't really rival this in terms of volume, because those will produce so much thrust and heat that you could never use millions of them a day on the planet. This system doesn't just get you into space cheap, it gets your whole civilization up there cheap, and lets you truly engage in bulk trade and transport. And that's always been the real goal, not to get a few astronauts to Mars, but to make it so cheap and easy that going to the moon is like flying to another country, and going to another planet takes as much time and money as an ocean cruise. So that's the series wrap-up on Upward Bound, getting into space. If those giant megastructures like Shell Worlds caught your interest, I'd suggest trying the Megastructures playlist, though you can skip the first 3 episodes since those are just quick overviews of what we covered in more detail in this series. Those are older episodes, so the graphics and audio quality are a lot lower, but the meat and potatoes are still there. If you're interested in some of the civilization aspects of folks who could build orbital rings, try the Advanced Civilization series, starting with arcologies. If you want to continue on past leaving this planet, try the Life in a Space Colony series. For alerts when new episodes come out, make sure to subscribe to the channel, and if you enjoyed this episode, hit the like button and share it with others. Until next time, thanks for watching and have a great week.